Swayam Prabha. Digital India. Educated India.
In the last class, we were looking at a very simple model which we called as bicycle model. We said that we will collapse the two tires of the wheels into one in the front and the rear, right? And define this model by means of 2 degrees of freedom. This is what we said. So that if this is the coordinate system, x and y, and z being, so I thought we did this like this, x and y, the z being inside the ground. This is the coordinate system which we saw, and we said that there are 2 degrees of freedom. U is not a degree of freedom, right? We said that it is the yaw rate and v, the velocity along the y direction. We said that the vehicle is traveling at a velocity u, which means that you are giving that velocity. So let me call that as u, that's traveling there. In other words, we are now looking at lateral dynamics when the vehicle is now taking a turn in simple terms, or we are into a maneuver. A number of things I want to clarify because there were questions at the end of the class. One is that what are the assumptions that we have made here, right? It's quite obvious, but let us put that very clearly. Now when the vehicle takes a turn, obviously there is going to be a roll. Okay, the vehicle rolls. Probably you would have heard about this term roll center, roll axis and all that. Okay, so there is a roll, right? And that roll is not taken into account in this case, obviously. That is not a degree of freedom in this model. So the roll is not accounted for. So in other words, all that load transfer that comes due to roll is not there in this model. I am not considering the wheels individually, so that the stiffness of the wheel, rear wheel in this model is nothing but the addition of the stiffnesses of the rear and the front wheel. Clear? That's the second thing that I'm going to do. The third thing I'm going to do, especially in this model, I can extend this definitely, in this model, is to consider a linear tire. So roll not considered. So I'm going to consider a linear tire model. I can remove that later, of course. Then I am not considering the compliances of various bushes and other things that come into picture. All those things I am neglecting. Okay, and we will bring in all those things later. In other words, what we are going to essentially do is to look at this model, derive the equation, understand the physics, and then slowly include, okay, the effect of those aspects which I have neglected right now. That's the whole idea. Clear? Obviously, there's going to be a load or force rather that's acting, which we call this as FIR and FIF, and that there is that's the delta, which is the the steer angle given, okay, and that is the alpha f. I mean, these are all exaggerated, so all angles are small. Okay, just to show you, okay, from the center, that is the delta that's given, that's the delta f, and that, what was that? V plus AR, where R is this distance. Remember that, that's the distance, and that distance is B. Okay. Then we said that that is beta. So tan beta is equal to V by U, which is approximately equal to beta. And then, okay, we said that delta minus alpha is equal to V plus AR in actual terms, as you look at it. But this alpha f is actually negative. In order to bring that into effect, we define that to be negative, right? So ultimately, if you go back and look at the expression which we derived, we said that delta is equal to L by R minus alpha f plus alpha r. Right? This is what was defined. There's a small confusion in this because there are textbooks which give this equation. For example, if you look at Carnap, vehicle stability, he gives this equation. If you look at Gillespie, okay, he gives another equation. The equation is slightly different. Okay? So, and there are other books, many books which give the equation differently. So they write that as L by R plus alpha f minus alpha r. Okay. So they give it like this. Now, there is a confusion, like which is correct. Both of them are correct. There's no, actually they are the same. The only thing is, this is the mod, you know, the actual value. Go back and look at the way we had written, okay. We now can write also, I mean, the variance of this is delta is equal to alpha f plus V plus AR by U. I can write it like that. Okay. So that now alpha f would become the actual value of this angle, and sine is not included. Right? But go and look at what are the way we had written. Or in other words, in this case what happens is alpha f is equal to delta minus V plus AR by U. Right? This is the actual alpha f. Actual alpha f. Now, how is that? How did we write it? Delta is equal to minus of, alpha is equal to minus of delta minus V plus AR by U. That's how we wrote. But on the other hand, we wrote alpha f is equal to minus delta minus V plus AR by U. Okay. Simply because that minus sign is given, because if I now consider alpha f, it is outside. Okay, it's like that, which is actually negative, and that's why this negative sign. So you can use both, it doesn't matter. But be clear about the angle and be clear about the force that results from that angle. Okay? So signs, if you want to be consistent, the signs are important, follow the correct signs. Or you know intuitively and so follow only the values. So in other words, you can write this as, if you're going to write that as like that, and then you say that it is just this value. In the same fashion, if I see the force Fyf, okay, it is alpha f is in this direction minus, okay, Fyf is positive. So if you want to follow the signs clearly, then you can write that as Fyf is equal to minus, okay, the constant which we called as C alpha f into alpha f. That minus sign is again because the physics brings that sign. One is negative direction gives a positive Fy. That's why it is. Right. If you don't want to follow this, this is confusing, okay, fine. Then you can write that as like this, but then this is the mod, then correspondingly you should substitute. In fact, if you put a minus here, notice that ultimately the force, nothing happens. So there's no difference, nothing happens. Because when I put minus alpha f, actually that's the sign. I'm following sign conventions correctly. When I put minus alpha f, obviously it becomes plus. So Fy is in the plus direction. Okay. So this is what this, there's no confusion in this, but many books follow, every book follows its own terminologies and the way it writes. And so you have to be careful on that. Clear? Any other questions? Fine. Now there was one more question which I said I will answer it later. Let's not be in a hurry. Yes, I'm going to answer that. But then before the class, I know some of you may have this doubt. What is this? You are talking about stability, and you said that I'm not right now not worried about eigenvalues. Okay, and I know that stability depends upon the eigenvalues. I know that I have to calculate the eigenvalues, and that if the real part of the eigenvalue is negative, okay, the system is stable. These are the things which I have studied. You suddenly say that don't worry about that. Let us first look at stability and then look at this. I thought there is a confusion. Though I clarified it, but let me put that for the sake of others. Yes, of course. But usually, pedagogically, you are absolutely right. Usually what we do is, if the values are given, if all the values are known, okay, and if I give this as an equation, when I substitute all the values, then it's easy for me to calculate the eigenvalues, and it's easy for me to find out whether the system is stable or not. But if I do not know the value, I want to develop a condition for it, I need not calculate the eigenvalues. So I will follow a stability criteria like Raoult's stability criteria and so on, and develop a condition, okay, which gives me stability. This is not in variance with what you are defining, okay, and we will also see later, a bit later, why, okay, the stability condition, what you learned is also important, and we will use that. But right now I'm not going into that because, as I told you, I don't have numbers. I now know the governing equation, okay. So I have to only look at that from that perspective. I have to develop the stability criteria. Clear? So that is why I said that let's first look at stability, okay, from a different perspective, okay, or in other words, same principles are same from a different angle, right? So for that, let me go back and see where I left. I had written this in the state space form, right? I mean, that's where we left, and we wrote that as V dot R dot. So that V and R is our the state equations, and so that this would become minus C alpha F plus C alpha R divided by M U minus AC alpha F plus BC alpha R divided by MU minus U minus AC alpha F minus BC alpha R divided by IU. See, I is nothing but the moment of inertia term, IZ term, okay, or IZZ or IZZ, however you want to pronounce. Okay. So that's what we had written in the last class. Right? From which we took off, we wanted to define what is the stability criteria if an equation is given. That's where we went about, right? And then we wrote down, you remember that we wrote down the differential equation for nth order system, right? I think we did all that. Clear? And then we took the, what's that we did later? We took the Laplace transform, right? And then we arrived at an equation, a Laplace in the Laplace domain, and so on. Clear? So ultimately we wrote down an equation for this as a naught s squared plus a1s is equal to 0. This is where we left. Right? Clear? Now, for this system, for the second order system, first and second order system, you know route stability criteria. I've done that in controls. I'm just going to not go into details of it. I'm just going to restate it, that the necessary and the sufficient condition for this system to be stable. Ultimately, this is the system which we are dealing with now. Okay, for a system to be stable, these quantities should be positive. A0, A1 and A2 should be positive. Okay? Now, in other words, if A matrix is A11, if A matrix is written as A11, A12, A21, A22, remember that I have to do at S minus Si minus A, okay, and so on, right? It's all done. Any questions? So this is what we are going to use. That is why we are not looking at right now whether eigenvalue, the real part of the eigenvalue is negative or positive and so on. We are not looking at that. Okay. So in this system, I'm going to write down, A0, A1 and A2, okay. Go back and look at it, and where A0, we had already written that. So A0, okay, can be, for example, ultimately looked at like this: A1 is equal to minus of A11 plus A22, and A2 is equal to A11, A22 minus A12, A21. Okay, so that is where it actually boils down to. Now I'm going to write that down. You know, from here we will take off. We will look at that. So A11 is my first term. So that is this term, and so on. A12, A21, A22, and so on. So let me now write down A1. A1 is minus A1. This is how, you know, I've normalized this as that A0 is equal to 1, and this is the equation. Okay, you can go back and look at that. So A1 is equal to minus of A11 plus A22, that is equal to C alpha F plus C alpha R divided by mu, okay, plus A squared second term C alpha F plus B squared C alpha R divided by RU. Right. Let's look at the second term, A2, or the third term rather. So A11 into A22, minus and minus, so that becomes plus. So C alpha F plus C alpha R divided by m into u multiplied by A squared C alpha F plus B squared C alpha R divided by IU. That's the first term, minus what is A12 minus AC alpha F plus BC alpha R divided by MU minus U multiplied by which term? That's the term, right? So I would put that as plus because there's a minus there, and so multiplied by AC alpha F minus BC alpha R divided by IU. Clear? Simplify this. Look at that expression and simplify it. Let's see what you're going to get. Take a minute, simplify it. So let's do that. A squared C alpha F first term plus B squared C alpha F C alpha R plus A squared C alpha F C alpha R plus B squared C alpha R squared. Sorry, that's right. So that's the expression C alpha R squared divided by M I U squared. Okay. We'll do a small jugglery here. Let me put that as minus. Okay, and write that as like this. A small jugglery I'll do. Okay, why am I doing this? Becomes simple. The first term now becomes minus AC alpha F minus BC alpha R whole squared divided by M I U squared okay, that is because there is minus, I had taken that out, right? Then next term minus U, because minus is there, minus U into AC alpha F minus BC alpha R divided by IU. Clear? Simplify this, expand this, so you will get, what's that you will get? So this will be A squared C alpha F squared plus B squared C alpha R squared, okay, minus, that is both of them are minus outside. So what will happen? This guy will go off and that guy will go off, okay, and you will get minus 2 AB alpha F alpha R, right? Clear? And minus, this minus is there, that will be plus. So you will have A squared, so I'll write that as A squared C alpha F C alpha R plus the second term B squared C alpha F C alpha R, and the third term comes from here, which will be plus 2AB C alpha F C alpha R, the whole thing divided by MI U squared. Okay, that's the first term. Then I have the second term. Let me rewrite that term. I'll remove this. I'll take care of all those minuses and say that plus, I'm adding that, all that A squared plus B squared and all that, this plus, what's the second term? BC alpha R minus, second term, AC alpha F upon I. Okay. Let me look at this carefully. It is A squared plus B squared plus 2AB. So C alpha F alpha R, I can take that out. So I will write that as C alpha F C alpha R into A plus B whole squared, which is L squared divided by MI U squared. So that is the third term, which I called it as A2. Right? Okay. Now let us go back and look at the stability. Right? I hope I've written correctly. Look at MI, rest of it I know it's correct. MI U squared. I hope I've not left anything. Okay. So now look at these three terms. The Rhodes condition says that these three things should be positive. Yes? The second condition, or the second one, sorry, not second condition, second coefficient, A1, look at that coefficient. Can that be negative? So that can't be negative because we said that C alpha F alpha R are all positive, M, U, everything is positive, so that can't be negative. Right, fine. But let's get back to A2. Okay, let's get back to A2. First term, no worry, that will be positive. But second term, it's possible that the second term is negative. Okay, so when AC alpha F is greater than BC alpha R, obviously this is going to be negative. Right? So the only possibility of the terms becoming negative is dictated by this guy here. Right? So as long as, in other words, as long as C alpha R is greater than AC alpha F, BC alpha R is greater than AC alpha F, do I worry? Nothing to worry. Everything is positive. On the other hand, if BC alpha R is less than AC alpha F, then this becomes negative. There's a cause of worry. It's not that the total sum becomes negative, but there's a cause for worry. That's all I would say. Right? In other words, this can be so high that the guy can overtake this guy and make A2 a negative term. All right? Not that just because this is negative, it has already, you're done and doomed. No. Clear? So this condition, we will later call this, okay, as an understeer condition. Why? How this term? All those things we will define. We will define shortly what is called as understeer coefficient, and we will define all those things. When BCR alpha R is less than AC alpha F, okay, then we have oversteer condition. Why not BC alpha F, BC alpha R is equal to AC alpha F? Yeah, sure, it's possible. And that brings out a condition called neutral steer. Now, why are we calling this as understeer, oversteer? You know, what is this condition under which it will really become unstable? These are the issues which are very interesting, right? And that's what we're going to see now. Now, let us rearrange this term and quickly get into a position where it will really become unstable. Okay? Rearrange the term. Look at that and rearrange the term and let me know when it will become unstable. So let me do that. Maybe I'll write that as A2 to be 1 by mi u squared plus BC alpha R minus AC alpha F divided by C alpha F C alpha R L squared multiplied by L squared C alpha F C alpha R. Let me do something like that. Okay, I. Okay. Let me take that I also out. I. Right? Let me bring another jugglery here. I'm just only manipulating this. It's all the same. Because I'm zeroing in on terms which are going to be important. So look at all these terms. They all cannot be, I want all these, this to be greater than 0. So these terms are good guys. They're all positive. Okay, so I'm not very worried about it. So my condition is actually 1. Let me do one more thing. I'll put this u squared here. Okay, and then put u squared like that. Right? So because u squared is positive, so no problem. So my term actually reduces to m into BC alpha R minus AC alpha F divided by L squared C alpha F C alpha R into u squared. Okay, that's how it reduces to, and that should be greater than 0. Okay, fine. As long as this is greater than 0, I have no issues. But if this is less than 0, then this term becomes negative, right? And at a point of time, cross 1, okay, and make this whole thing negative, right? So let me call this as, say, K3. Why K3? I'll tell you why I'm calling that K3 a bit later. Let me call that as K3. Okay, so that I will write this as 1 plus K3 u squared, okay, to be greater than 0. That's the condition. And ultimately, this reduces to a condition where K3 becomes negative, okay. So u squared, yes. So when u squared is equal to root of 1 minus of K3, okay, that's where when K3 is negative, this is the condition you would get, okay. When K3 when K3 is negative, u squared is equal to root of minus 1 by K3 is the condition beyond which, not u squared, sorry, u, beyond which the vehicle is going to be unstable. Oh wow, that's a very interesting conclusion. Clear? So in other words, what happens is that entry of the term u here in that expression. Right? So what does it mean really? Let's physically understand it. We'll go into the equations a bit later. Okay? So there's a K3. Look at the K3 carefully. Okay? K3 consists of m, characteristics of the vehicle, no problem, it's going to be a constant. Okay? A and B, what are A and B? The distances from the center of gravity to the front and the rear, right? Alpha F and C alpha F and C alpha R are the result of assumption that the tire is linear. Clear? Linear. So they are constants of the tire. L squared, C alpha F, C alpha R, and so on. So that makes this whole thing K3 to be a vehicle parameter. Okay. So the vehicle can be an understeer vehicle or an oversteered vehicle. When the vehicle is an oversteered vehicle, K3 becomes negative. Immediately it doesn't become unstable. K3 becomes negative. Okay, I have not yet defined why I am calling this as understeer, oversteer. That we will come in a minute. Okay, so that plus into K into u squared simply means that the oversteered vehicle has a velocity at which this third term goes to negative or becomes negative, and that velocity is called as the critical velocity, above which the vehicle is going to be unstable. Okay? And what is this instability going to cause? That also we will see in a minute. Okay? So that is called as the critical velocity. Why I have put this as K3? Because I am going to have two more definitions, K1, K2, K3. There are books, I am not sure, I don't have the list, but I know that some of the books, okay, call this as an understeer gradient. Call this as understeer gradient. Okay. So that they would write this as 1 plus K3 u squared and K3 being an understeer gradient. Why am I being careful and write K3? Because this definition varies from one book to the other. Okay? The concepts do not change, but the definition changes. Another book would just simply state L. They'll remove that L and say that is understeer gradient. Okay? So we will see why the other books say like that. So this is a simple way of defining this understeer gradient. Right? Okay. So that's one thing, the first thing that we have. But why did we call this as understeer and oversteer? Okay? In order to understand that, let us get back to our original expression, okay, and treat a steady state condition for the body or for the vehicle. Okay? Let's get back to our original governing equation. All of you remember the original governing equation? How did we write? Okay, can we remove this? Any questions? Clear? Yeah? Good. So remember that in the very first class, I have to get back, I think we called it as 1 and 2. Iz r dot, what was the expression which we wrote for this? Iz r dot. You remember? That's the first thing you wrote. A into fyf minus b fyr. Right? And what's the second expression we wrote? M into v dot plus ru is equal to fyf plus fyr. This is what we wrote. Let us now consider what is called as the steady state condition. What is a steady state condition? What do we mean by steady state condition? What we mean by steady state condition is that there is no time derivative terms. Okay? So that I will write the first equation to be A fyf minus b fyr is equal to 0 and m ru is equal to fyf plus fyr. Right? These are the steady state terms, or sorry, steady state equations. Let us now get back to my delta terms, delta what I had written here. Okay? Write that down how we wrote it. I hope there's no confusion on that. I can write this in two ways. As I said, I can write that as L alpha f minus alpha r plus L by r. Right? Okay. Now, what I'm essentially going to, what is that I'm going to do? Before we go further, let's understand what we're going to do. Now, I am going to look at the effect of delta, effect on delta due to the new introduction or new term which we called as understeer gradient. Okay? Now, I'm going to look at how that delta is going to be affected. Okay? How in a steady state maneuver, okay, where we have simplified the equations and we're going to look at how that's going to have an effect. This is what I'm going to do. Right? Okay. Let's look at the first, this equation, MRU. What is MR? What is R? Remember that it is the yaw velocity, and so it is equal to U by capital R. Okay? And so m U squared by R, and that is equal to fyf plus fyr. Right? Okay. Note that I can also treat this as minus alpha f plus alpha r. So, I mean, I have to be careful in that. Note that carefully. Right. Now, let us look at the geometry part of the vehicle motion. Okay. Here it is. So, we define very clearly what is capital R and so on. So, obviously, that is the radius. That's the radius of the turn. 1 by r is actually curvature, right? We know that. Okay. So, I have that angles, what's this A and that's B, approximately. There's a lot of it are approximation because every angle is small and all those assumptions we make. So that angle is what? What's that angle? Okay, and that angle is B by R. Clear? Okay, and L is actually the total length of the vehicle. So that is the geometry which is the the vehicle takes when it takes a turn. Right. We have to go through a number of smaller things so that we understand it clearly. One thing we know from our earlier classes, how my normal force is distributed. Okay, remember all these equations. I'm going to use them here and there. Okay, maybe in the next class when you start, we will write down all those things. Okay, so have your notes ready so that we will, when I put down an equation, you will go back and refer to from where we are getting it. Now, I know that W front, which is the normal load that acts on the front, is equal to in this way. What's it? B divided by L into W, right? And the W rear is equal to A divided by L into W. Okay? Now, if Fy is the total load that's acting, obviously the same. How did I get that? By taking a moment, okay, about the center or about one side and so on. The same thing I can do it here as well. Because this is steady state, I have no issues on taking the moments, and hence Fyf is going to be distributed in the same fashion as B by L into Fy, and Fyr is equal to A by L into Fy, where Fy is actually the total force that's acting. Yeah, any questions? Okay, so it's first thing is interesting to note that the lateral forces are distributed in the same fashion as that of the weights, which I can write it as m u squared by r to a, that's Fy, okay, sorry, into b by l. That is m u squared by r is Fy, the total Fy, and that is equal to m u squared, this is u squared by r into a by l. Right? Now I want to use this. Can I use that? Not very difficult. This is nothing but mg, and that is mg. So I can substitute that into that expression and rearrange the terms in order to, and get Fyf. Why am I doing it? That will become clear in a minute. Okay. So in other words, the first thing is that the lateral forces are distributed in the same fashion as that of the normal loads. Okay? Rearrange it and tell me how I can write that in terms of Wf. M into B by L, so W by G into U squared by R, is that right? Same way, Fyr is equal to Wr by G into U squared by R. Okay. I took some time to get back to these two things. Okay. Now we'll go fast. We will start from here and then we will substitute that into delta, we will see what happens, and so on. Right? Okay. The only thing is that there are a number of equations. Please go through them. Okay, if you have any doubts, ask me in the next class. I'm going to use them now, okay, to bring out the physics. So you should be clear with every equation that we had written. Right? We'll stop here and we'll continue in the next class. Yeah.
Assuming lateral force distribution is same as
Yeah, right. So that's why I said that it's an exaggerated figure and that it is all those angles are neglected and then that the forces are distributed something like this and like this. Okay? That's all.
Velocity u equal to constant to rho.
Oh, yeah, of course. U is
Will be having
what?
some lateral forces which will be reducing the velocity. Longitudinal force.
No, we are not looking at longitudinal forces. This is a lateral force alone is what we are looking at. Okay? So we are not looking at longitudinal forces. The three equations, if you remember, we wrote, and Fx equation we are not considering. Okay?